RTK is normally used to enhance the positioning accuracy of GNSS. With an RTK capable receiver, you can measure your position with centimeter level accuracy. RTK is normally most useful when it comes to land surveying and other applications where you need to know your exact position. One of the most annoying and random error a GPS signal can experience is atmospheric error. Lower frequencies are more affected than the higher frequencies. A standalone GNSS receiver cannot solve these errors. So a GNSS receiver cannot provide positional accuracy better than a meter. RTK resolves these errors by using a second GNSS receiver located nearby. So a typical RTK survey consists of two GNSS receivers. One is a base station, another is a rover. A base receiver is static and placed on a predetermined location. Remember, your position is as good as the accuracy of your base station coordinates. A rover receiver is movable, and that's the receiver we use to collect our data. The idea is if we have two GNSS receivers close to each other, the atmospheric error in the signal that they receive are almost identical. As a result, they can be excluded from the calculation. By eliminating all these atmospheric errors, a rover receiver can better estimate all the ambiguities in its positional calculation. The base receiver transmits its position and observed satellite data to the rover station. The rover uses this information to exclude the atmospheric error from the calculation and better estimate position. Still, having a second device is not enough to have a centimeter level accuracy. Another essential part of RTK technique is a complex mathematical algorithms. Let's look at what the RTK calculations consist of. First, there is pseudo-range measurement. The pseudo-range is an estimated range between a satellite and a receiver. Knowing the time the signal was sent and received, the receiver calculates the distance to the satellite. However, the pseudo-range measurement is not very accurate way to find the distance. One of the obvious error is called a Sagnac effect. As the earth rotates, by the time the signal was generated and when it was received at the receiver would have moved due to earth rotation. And there are many such errors. This brings us to carrier phase measurement. In this process, we just use the carrier frequency and discard the data in it. The carrier phase is actually the more advanced way in calculating the distance between a receiver and the satellite. The radio signals from the satellites are traveling in a sinusoidal waves to the receiver on the ground. With the carrier phase measurement, we can understand where exactly we are in that particular phase. This is done by resolving the number of cycles in which the signal is transmitted and received by the receiver. This can be achieved by using a combination of differential GPS correction data, transmitting GPS signal phase information, and ambiguity resolution techniques via statistical test in real time. The period of the carrier frequency times the speed of light gives the wavelength, which is about 0.19 meters for the L1 carrier. With a 1% of wavelength accuracy in detecting the leading edge, this component of pseudo-range error might be as low as 2 millimeters. This compares to 3 meters for the CA code and 0.3 meters for the P code. And all these are happening for all the satellites that the receiver receives in real time. And if your GNSS receiver have all these frequency capabilities, then the distance measurement from the satellite to your GNSS receiver will be very, very accurate. So the question is, how far can a rover go from the base station? Well, for a single band L1 receivers, the maximum baseline distance is about 10 kilometers. And for multiband L1 and L2 receivers, the max baseline length can be about 60 kilometers, assuming that atmospheric conditions are same at both the places. And of course, the distance depends on the transmitting radio capability, line of sight, local area conditions like open field or urban area with lots of background electromagnetic noise pollution. You can also opt for signal transfer over 3G or 4G network, which can eliminate the localized disturbances and line of sight problem. It is also possible to receive the correctional data via network utilizing a protocol called NTRIP, networked transport of RTCM via Internet Protocol. This method, however, requires a constant connection via a GSM modem or a smartphone and a subscription to your local NTRIP service provider, who will have an infrastructure of fixed base stations forming a national or regional grid. One of the main advantages of NTRIP is that it uses a network of RTK base stations that are already in place and therefore has no range restriction. This is very ideal for a survey area near coastline or even inside a river or channel where you will be more than 10 kilometers from a single fixed base station. Using an NTRIP solution, you can expect your position accuracy to be within plus minus 2 centimeter. If so happens that you cannot get NTRIP or a good radio or 4G signal during your survey, then you can use something called a PPK system. PPK stands for Post-Processing Kinematic. Here you can survey on some predetermined points without the RTK signal from the base station. Your base station and rover will log the data separately, even though they have no real-time connection between them. Later on, you can combine both this data together in the computer and get precise position for your RTK survey. And this is known as Post-Processing Kinematic or PPK. Of course, you will require a software to do that. Just say, "Hey Google, hope we learned something new today. I thank you for being here with me."